Okay, guys, so let's look at some pictures. And so just a quick review, SPDF, those are our sublevel types. They are identified, if you will, by shapes, S being spherical, P's being dumbbell, F's being cloverleaf, and D's being cloverleaf, and F being complex. And so let's look at some pictures. All right, so here's an S orbital. And so you can see that it's round. And right in here in the middle would be where the nucleus would be. Just a little pinpoint would be the nucleus. Nucleuses are very small. So a little bitty pinpoint, and then that ball is simply the orbital. That's the region of space around which the electrons are located. Somewhere in there. We don't care where they are. They're just in there somewhere. Now let's look at a 2s, because remember, the S sublevels can appear on all energy levels. Go back to our chart there. S sublevels appear on the first, S appears on the second, third, fourth, fifth, sixth, and seventh. And so S sublevels are on all. So we can look at a 2s orbital. And you will see here that the blue orbital is the 2s. Now, if you look at the cutaway, the red, that would be the 1s. And so the 1s is small, the 2s is bigger. Because it's on the second energy level, it has more energy. It's a bigger orbital. And the 1s is inside of it, kind of like those Russian dolls that nest inside each other. And so the 1s is small, the 2s is bigger. 2 electrons in each of those orbitals, 2 in the 1s, 2 in the 2s orbital. Now, p's, we said, are dumbbell shaped. And so here is a look at p orbitals. Now remember, p orbitals, they're on energy levels 2, 3, 4, 5, 6, 7. And p orbitals are dumbbell shaped. And we said that there are 3 orbitals. The math solution produces 3 results. And so we see 3 orbitals here. The difference is that they are oriented differently in 3-dimensional space. So that goes back to the magnetic quantum number, the 3D orientation of the energy level sublevel shapes. So it's tying it together. The 3D orientation changes with different energies. And so back to our picture, there we go. So one on the Z, one on the X, and one on the Y orientation. Now, let me make sure you understand this, because this is important to understand. These are all on the same atom, and so I'm going to do some drawing here. And so what you see on the computer screen is you had a p orbital here. That'd be the py. You got a px dumbbell. That's not very good, but you get the idea. Py, a px, and you would also have a pz, where it lies on the z-axis. So that's what you see in this computer generated, but they're all together. They're all together. Then this is the nucleus. It's one nucleus. It's one atom we're looking at. And so you combine them, and what you get is you get a nucleus in the middle with a px, a py, and actually I went the pz the other way, but that's okay. There's the pz. And so it's 3 p orbitals in the third or in whatever energy level we're looking at, with the nucleus in the middle. And so this is like an exploded view. We're taking the individual orbitals apart, and we're getting these 3 pictures. That's a very important idea to understand. We can look at a D, and here are the 3 Ds. So I told you that Ds are 4-leaf clover shaped, so this one right here, bottom middle, kind of gives you an idea of the 4-leaf clover. And this is important to understand. This is one orbital. There are 4 parts to this orbital, but this is one orbital. It's not 4 orbitals. It's one orbital. Somewhere in this orbital, at most, we can have 2 electrons among these 4 parts to it. So this is a quarter of the orbital, 1/4 of the orbital, 1/4 of the orbital, 1/4 of the orbital. Just like the P's, this is one orbital. It's got 2 parts to the orbital. That's half the orbital, that's half the orbital. And so that's an important thing to understand, that it's one orbital. So here are your 5 d orbitals based on your 5 orientations of space. Now, 4 of those 5 are your 4-leaf clovers in various orientations. The fifth one is this, it looks kind of like a P with an above and below lobe, and then you got this donut going around the middle of it. So that's your Ds. Fs are, we said they're complex. They're a little more complex. Here you go. They have multiple lobes. These things are called lobes. Again, this is one orbital. There's 7 of them. 1, 2, 3, 4, 5, 6, 7. 7 orbitals. Each of these 7 orbitals can hold 2 electrons. And so if you take all these together, that makes up a D sublevel. So the D sublevel has, back up here, the D sublevel, I'm sorry, that's the Fs. These are Fs, not Ds. Sorry, made that mistake there. These are Fs. So if you take a look at your F sublevel, you have 7 orbitals. Each of those 7 orbitals can have 2 electrons, so 2 times 7 gives you the 14 electrons possible in that F sublevel. Now, again, these aren't separate. They've been exploded out. They've been separated so you can see the different shapes. If they were all together, you wouldn't see shapes. It'd just be this big, massy blob of, you know, whatever it would be. And that's an important idea to understand. And that's kind of where we're going to wrap up here, is that when you look at the atom, here's our nucleus. The lowest energy would be the first energy level, and in that first energy level you have S sublevels, and S sublevels are spherical. So I can only do 2-dimensional here, but this should be a 3-dimensional ball around the nucleus. And that S can hold 2 electrons, if you remember. So if we have more than 2 electrons, we have to go to further away energy levels. So we go to the second energy level, which is also a ball, which surrounds the nucleus. But it not only has the S, it also has the P, which is the dumbbell-shaped one. So we got the py orbital, we have the px orbital, and we have the pz orbital. And if we have more electrons, we got to go further away. We have to go to the 3s orbital, which would also have an s, and then also a p, which would just be simply bigger. As we get further away, the orbitals get bigger. They maintain similar shapes, they just get bigger. And then these orbitals are electrons. And then we'd also, in the third level, have the Ds, the clover leaf. So I'm just going to do one of the clover leaves. We'll do a 4-leaf clover here. And then if we go further out, even change colors. We would go to another one. And we'd also have Ps there. And D clovers. And then we go out another one. And we get another further away S, and bigger P's, and bigger D's, and we have a bunch of D's. And so here's what you get. This is kind of an important thing. You just get this big mass of electrons, which we call the electron cloud. But the thing is, in that electron cloud, there's a great deal of detail and specificity of where the electrons are. They're not just everywhere in there randomly. They're located in very specific locations based on these probability barriers that the Schrodinger equation gives us, and they are confined to those locations basically. They don't have to be there all the time, but they're effectively confined to those locations in those regions. We don't care where they are exactly, we just care that they're in there somewhere. And so that's the important thing, is that if you get into the detail, there's all kinds of detail, and that detail is described by the 4 quantum numbers. You could describe an electron with the 4 quantum numbers. You could say, for example, the first number is n. N is the first quantum number. L is the second quantum number, like the x and y. They're just variables, n, l. And then the magnetic quantum number is m sub l, and the spin number is s. And so I could say, hey, n is 2, l is 1, m sub l is -1, s is +1/2, and that tells you a specific electron you're talking about. Well, it's in the second energy level. It's in the sublevel p type. That's what this would be. That'd be a p-type sublevel. It's in a particular orbital of those p sublevels. Remember, p has 3 orbitals. It's in a particular orbital that's designated the -1 orbital. And then it has a particular spin. Is it spinning clockwise or is it spinning counterclockwise? Well, the +1/2 would mean it's spinning clockwise. And so you can get very detailed on the electrons instead of just saying, well, it's in, 8th grade says, hey, it's in this ring. There we go. We got an electron in that ring. No, there's a lot of detail that can be pulled out of that besides that. And so there is your basic lesson on quantum mechanics. This is what we did on Monday. And so particularly you guys who are on the band trip, what you really need to focus on is making sure that you know the data in these two graphs, or these two tables, not graphs, and know it. You just simply need to memorize it. For example, I can ask you, hey, what sublevel types from the third energy level? Well, in the third energy level, you have SP and D sublevel types. Or I could say, or I could ask you, oops, which way am I going? There we go. I could ask you, what's the shape of a D sublevel? Oh, D sublevels are four-leaf clover shaped. Or I could say, how many orbitals are in a P sublevel? Well, there are 3 orbitals in a P sublevel. Questions like that. And then I could even go a little more complicated. And I could say, for example, how many electrons, I could say, how many electrons in a 3p orbital? And that can be tricky if you're not paying attention. Again, the 3 and the p are just labels. That means I'd be talking about the third energy level, that's the 3. I'm in this third ring, I'm in the third energy level, and the p tells me I'm in the second sublevel, if you will, but I'm talking about an orbital. I'm just labeling an orbital 3p. Any orbital can have 2 electrons. Now, if I asked, how many electrons can there be in a 3p, not orbital, but 3p sublevel? Well, now we go back to this table here. A p sublevel has 3 orbitals, which would have 6 electrons. Or I could say, hey, how many electrons are in a 3, or how many electrons are in the third energy level? Third energy level. Well, in the third energy level, has S, P, and D orbitals. I'm sorry, S, P, and D sublevels. S orbitals have 2 electrons. S sublevels have 2 electrons. P sublevels have 6 electrons. D sublevels have 10 electrons. The third level has all 3 of those, so it would have 10, 6, and 2. It'd have 18 electrons. So being able to reason out questions like that, which is based on, do you know these tables and how they interact and interplay with each other? Okay, so good luck on your competition, and we'll see you in a few days. I'll probably post another video up tomorrow. We are also going to have a quiz on the history of the atom, the history of the atomic models, if you will. And so you need to be studying while you're there also your scientists, their experiment, their discovery, and what their model of the atom was. So for example, I could ask you, who discovered the electron? And you should answer J.J. Thomson. And so make yourself some flashcards, quiz each other, and make sure you understand those things. We're planning on a quiz Tuesday. And so you have to make that up when you get back. Have fun.